Good evening, everybody, and thanks for showing up for this tutorial. As you can see, it's going to be an overview of quality of service in packet-based IP and MPLS networks. I am Arun Satyamurthy, and with me is Utpal Mukhopadhyaya. The third person, Paresh Shah, couldn't show up today, and so it's just going to be the two of us. Both of us are we are part of the software engineering team in the core routing platform at Cisco Systems. Just an introduction about us. So let me briefly go over the agenda. We'll be talking about quality of service, focusing on IP and MPLS. We will introduce about the motivations for implementing QoS techniques, and then focus the discussion on IP diffserv, the terminologies in diffserv, the RFC pertaining to IP diffserv. And then Utpal will take over and talk about MPLS QoS, go over the experimental bit, the MPLS tunneling modes, and discuss briefly about traffic engineering, and wrap it up with the diffserv aware traffic engineering. This we would like to encourage a highly, as other sessions have been, please keep it as interactive and interrupt us with questions. And if there are any inaccuracies, please point them out as well as we go along. So going to the introduction, a quick look at the definition of quality of service. As most of you would be familiar with this concept, it's a series of techniques essentially to manage a set of resources, a set of parameters, so that the traffic is provided in a manner that is expected, in a manner that is guaranteed. And the parameters that we seek to control and manage would be the network bandwidth, delay, jitter, and packet loss. We will be briefly examining about these different parameters and how to control them as well as we move forward in this discussion. The first aspect is to characterize traffic. There are different types of traffic out there. There are different sources from which they emerge from, different destinations they go to, different requirements. There are, again, real-time and non-real-time traffic. Some of them are sensitive to delay. Some of them are bandwidth intensive. So all these aspects have to be considered when planning capacity, when designing network, and making sure that the traffic guarantees are met. The three types of traffic that are out there today include data, video, and voice. And the characteristics of these type of traffic, again, would depend on them being bursty, constant. And as we talked about in IP, we have V4 and V6, and there's MPLS as well. So that's how different traffic types are out there, and we need to understand how they behave and what are their requirements before we try to influence the parameters that need to be acted upon on them. So the QoS requirements, as pointed out in the definition, is the three parameters: latency, jitter, and loss, that needs to be influenced on these traffic types that we just talked about, so that end-to-end QoS guarantees can be provided. In the network, there are finite resources. The resources would include memory and the router, which in turn translates to buffers, the queues that are out, and then the scheduling mechanism. The finite resource management is, again, pivotal in ensuring quality of service. And so they go hand in hand in ensuring the traffic characteristics are maintained by managing the resources. This in turn translates into how the service level agreements are come up with and how guarantees are provided between customers and providers. Also, you could have small number of flows going across the networks, or you could have thousands of flows, and how you manage them also defines the models which we will eventually be talking about. So the managing of the flows, whether it's in a smaller level or in a large scale level, is also another aspect that needs to be considered. So this is sort of an illustration of how the three pieces that fit together: identifying the traffic types, determining the parameters that influence the traffic types, and then coming up with a QoS technique that will ensure that the corresponding traffic type is appropriately handled. So this leads to two different approaches. There could be small individual flows going end to end for which certain guarantees are required so that the traffic characteristics can be maintained. Or they could be a combination of flows that belong to the same traffic type, belonging to a particular source, or needs to have a certain characteristic so that they could all be made to fit into an aggregated flow. So that by differentiating these two high-level aspects, we move to the next aspect of the discussion, which is talking about the service models for coming up with the QoS techniques. Although I mentioned two, there is one very elementary service model which is best effort, apart from the two other, which would be the integrated services and the differentiated services. The prime focus of this discussion is going to be differentiated services, but I'll briefly touch upon the first two as well. Best effort mirrors the way the internet emerged. No QoS, no guarantees. At the layer 3 network and IP, it's connectionless, it's best effort service, and that's the model that it originally came up with. And then emerged the integrated services model as defined in RFC 1633. Integrated services is in the other end of the spectrum where it tries to provide hard guarantees in the bandwidth that can be provided. So this involves a series of mechanisms by which it has to ensure that the path in the network can guarantee the network bandwidth for the particular application. And so integrated services relies upon a signaling mechanism in order to establish the reservations needed. And it uses RSVP, Resource Reservation Protocol, to be able to query the network nodes in the path to find out if the network nodes have the resources, if so, if they can assure the guarantees that are required. So that's the premise of integrated services, and it needs to be configured on every router in the path. Now, this premise also leads to one of its drawbacks. Every node has to maintain a state information so that the guarantees can be provided. Now, if there are a few hundred flows, then the network node can scale to accommodate that particular state information. But if there are thousands of flows, the network node becomes overwhelmed in trying to maintain the state information. And so scaling is potentially one issue where integrated services might slow things down. However, the newer trend is to aggregate integrated services information as well. But that's a topic that's not relevant to this discussion, but it is moving in that direction. And the next model that we call the differentiated services model was the third model, which fits in between the two ends of the spectrum. Again, it was defined in RFC 2475. The idea here is to aggregate the flows so that you can combine them at the edges of the network. So all the handling and the processing tasks are done towards the network nodes at the edge. And then that information is propagated to the core. So the core is more worried about scheduling, queuing, and certain core tasks. And it's not bogged down with the complexities of classification. So that's how differentiated services separates the two aspects of it. It tries to create classes of traffic types that are similar so that actions that need to be performed on those classes of traffic can be carried out appropriately. But the problem with differentiated services is that you could have various domains implementing their own behaviors on the traffic classes. This leads to an incongruence in the way end-to-end QoS guarantees can be provided. The other aspect is that if there is infinite bandwidth, obviously there is no need for QoS. Differentiated services comes in when there is a resource contention. You need to be able to differentiate between different types of traffic and then try to see what traffic type can be accorded a higher priority. So that's where there is a trade-off that happens when you plan for capacity and you end up in a scenario where there is a lot of congestion, and then you, in order to prioritize this congested environment, you come up with this differentiated services model. So this is a diagrammatic representation again of how the differentiated services architecture is about. Some of the key terminologies involved in it is at the edge of the network, as you would see on the ingress node and egress node. We have what is called TCA, or the Traffic Conditioning Agreement. What TCA does is it tries to prepare the core for the different types of traffic. The differentiation happens at that point of time, where it tries to classify the traffic types and it conditions it so that the core can do what is called per hop behaviors that are assigned. It doesn't mean the per hops behavior cannot be done on the edge. It can be done there as well. But the main activity done at the edge of the networks would include the conditioning part of it. We will briefly examine as to what the different techniques are involved in the traffic conditioning part and the per hop behavior as well. So the traditional model relied upon the task byte and the IP header. It had the 3-bit IP precedence value that it was originally used for, but it was only giving you 8 classes, and so it was felt that the classification schemes weren't sufficient enough to allow more granular differentiation mechanism, which is why the differentiated services code point byte or bits was introduced as part of the DivServ architecture, which proposed the 6 bits instead of the 3 bits, and the 6 bits were referred to as the behavior aggregates. So this is a representation of how the 3 bits of the precedence evolved into this 6 bits from the task byte as defined in RFC 2474. So there are 8 classes that we see on the left table. We see the 8 classes from the precedence. What DSCP introduced was labels or tags that explain different drop mechanisms or different differentiated characteristics, how you can classify traffic. There are 4 assured forwarding classes, referred to as the AF classes, and then the EF refers to the expedited forwarding, and then we have the best effort class. So that's at a broad level how the classifications have been arrived at, so that the operator or whoever configures the node is able to classify them the way they want to, and they will be able to establish different levels of service, so they can probably base their revenue models on how they arrive at the classification for those 4 that are listed, for the assured forwarding and then the expedited forwarding. Also, the differentiated services code point has been constructed in a manner to maintain the backward compatibility with precedence. So apart from the AF and the EF, there is this class selector set of fields which maps identically with the precedence values. And so it goes from CS0 through CS7. So that again maps to the 8 classes of the precedence to keep the maintain the backward compatibility. So the other terminologies pertaining to differentiated services would include, we looked at the traffic conditioning part. So there are certain elements that belong to the traffic conditioning part. So as traffic enters the network, the traffic conditioning aspect of differentiated services architecture kicks in, where it tries to identify what the traffic types are and how to manage them. So in an effort to do that, the first element that kicks in or that can be used would be the classifier. The classifier is again going to look into the packet and determine how to classify them. Once the classification happens, you then want to meter them. Metering is essentially a tool for informing the node about the compliance of the traffic to the rate that has been specified. The guarantees that the customer and provider come up with, the meter makes sure that the guarantees are met or not. It informs the subsequent processes that belong to meter, which would be the shaper and dropper, whether the traffic complies to the configured rate. And you have one other aspect called marker, where if you have one application where a marker comes in handy is if there is a non-complying traffic that meter determines, you can remark it to a lower value in order to penalize non-conforming traffic. So that is how, again, that is another aspect of conditioning at the network edges in order to preserve your bandwidth resources towards the core. So here's a brief look at classification and marking. In the IP packet, there are various fields that the classification, the classifier element can look into. Typically, a flow would involve 5 parameters, end-to-end flow, as explained in the source and destination addresses, the source and destination protocol, the port numbers, and protocol, and also the precedence and DSCP fields. So those are some of the key elements that the classifier can use and try to differentiate traffic that ingresses on the network edge. And marking, again, you can have packet marking on the precedence or DSCP in order to indicate a higher level of priority or a lower level of priority. Referring back to the penalization thing, if a packet comes in with a certain precedence, say 3 or 4, and if it's a non-conforming traffic based on the metering's output, you can lower the precedence value so that subsequent actions take note of the lowered value and they probably assign lower resources for the non-conforming traffic. So at the layer 3 level, the precedence or DSCP could be remarked. And as we examine the MPLS QoS part of the discussion, we will see how experimental bits of the EXP can be remarked. And there are also instances at the layer 2 level where you have the frame relay or the ATM header with the remarking capability in them. Again, going back to metering, this does not alter the traffic characteristics. Metering uses a form of algorithm called the token bucket algorithm to specify the rate at which the packets are arriving at, and in turn inform the two aspects of metering, which would include traffic policing and traffic shaping, that the rate, to notify them of the rate value. There are 3 parameters that the token bucket algorithm uses. The first one is the committed information rate. That's a configurable value where a particular node is configured with the rate information that should not be exceeded. And then there are 2 other parameters which would include the conformed and extended burst size. Again, this is going back to the different traffic type discussion where the nature of the traffic flow could be versely constant, and to accommodate any transient spikes or bursts, there is a burst parameter that the policer or shaper can be configured with, which the token bucket algorithm allows the provision for. So so metering, like it was pointed out, policing and shaping use the metering's output. And the key difference is policing is more of a rate, both are rate management techniques. Policing drops any excess traffic and it accommodates bursts, but then you specify a certain committed information rate, and that's the rate that's available. And anything exceeding or non-conforming, it's potentially dropped. Or it could be arranged for remarking as well. Whereas shaping introduces a buffering capability where it again tries to maintain the rate information that's provided in the CIR, but it increases the latency because of buffering. Any non-conforming packet gets queued up, and whenever there is resources available, those packets are sent out, but at the cost of increasing latency. So this is an illustration of the differences between the two. So you see the nature of the traffic is captured in the police, except that it's chopped off to provide the committed information rate, whereas shaping smooths out the traffic, and mainly because of the buffering capability. What this illustration does not capture is the bursts that are accommodated through the conformed and exceeded burst parameters that are provided. So that's not really captured very well here, but it does explain some of the obvious differences, the two elements of metering that it can provide. Policing again uses the token bucket scheme. We have a configurable parameter called the committed rate. It uses, going back to the token bucket scheme, there is a bucket-like illustration to it, and tokens are populated on it based on a certain fill rate. The tokens correspond to the packet size in terms of bytes, and the capacity of a particular bucket is determined by the burst size that it can accommodate. And as long as there are tokens in the bucket, whenever there is traffic and packets coming in, it could be sent out. And once the tokens are exhausted, and if you have packets coming in, that's when you have the non-conforming behavior kicking in. And when there are packets out there and there are no tokens, you can have the non-conforming behavior, whether it could be dropping the packets or recoloring the packets to penalize them. You can make it kick in at that point of time. So this is the illustration I was talking about. So that's the illusionary bucket that you have with tokens at the top that represent the rate at which the committed information rate has been configured to. And the burst size is the capacity of the bucket. And again, there are the conform and exceed actions that it lists out. Shaping, as again we've seen earlier, it uses the token bucket scheme as well, except that the buffering or queuing kicks in when there is non-conforming traffic. It again goes back to the availability of tokens for sending packets out, and whenever you don't have tokens, the queuing aspect kicks in. This is a similar illustration for traffic shaping. So DiffServ architecture, there are two aspects to it. One was the traffic conditioning part at the network edges, which we just saw. The second aspect is the per hop behavior. So the per hop behavior determines what actions need to be done after the classification is carried out. There are two aspects to per hop behavior. One is the queuing and scheduling and how to prioritize traffic. The other aspect is packet drop capability. How do you manage congestion, and how do you determine what packets to drop and how to drop and when to drop? So that essentially are the two main ingredients of the per hop behavior aspect of DiffServ architecture. As listed in the queuing techniques, there are various aspects to it: FIFO, weighted fair queuing, modified weighted round robin, and modified deficit round robin schemes. And then the congestion avoidance schemes would include the random early detection and weighted random early detection. Again, there could be many techniques. We are just highlighting a few key elements of them and just briefly touching over how they behave and how they are configured and so on and so forth. Queuing and scheduling, once you have classified the traffic, if you have numerous flows, now you have assigned them certain priority levels based on the precedence values or the DSCP values. Now you have to determine how to accord, based on the queuing resources that you have, you might want to determine how to prioritize certain classes of traffic, and so that you accord them more share of the dequeuing capability, and so that there would be impact on the other flows, but you try to minimize them by assigning weights to lower weights to other queues, so that the dequeue happens for those queues that have larger weights, and there'll be a lower amount of dequeuing for those queues which have lower weights. So this is essentially a prioritization mechanism among the many flows that enter a particular node. The other aspect that we talked about was the congestion avoidance mechanism. By default, when you have a queue without any specific congestion avoidance technique, there is a queue gets filled up with packets. It has a certain amount of queue length based on the buffers that are available. And once the queue fills up, any more traffic that arrives into the queue will not be enqueued. As a result, they are dropped. So that's a default queue mechanism, and it is referred to as tail drops. But we need a more proactive means by which queues can be managed for drop mechanisms, and that is one aspect which we will be shortly looking into. Today in the internet, most of the applications, they use the transport protocol TCP. That's the most dominant protocol that's out there. And in order to influence TCP characteristics and the adaptive end-to-end nature of it, we needed a more proactive means by which drops can be arranged for, and which leads to the random early detection and the weighted random early detection. But before we go into that, we'll briefly look at how congestion impacts network performance. When there is the aim of the per hop behavior is to be able to control congestion. But what happens when you don't have any specific technique is uncontrolled congestion. And as you can see from the illustration that the traffic peaks, but as the buffers fill up, as the queues fill up, and when it's not able to accommodate any more packets of traffic, there is the packet drop starts kicking in, tail drop essentially starts kicking in, and there is a big drop in the network performance in terms of forwarding capability. So this problem aggravates and builds on itself, and so we need a means by which we can control congestion. TCP uses the slow start mechanism. It uses the congestion window and receives feedback from the receivers to be able to vary its congestion windows. So if there's any drop in the network, it is one of the things it indicates is there is a congestion in the network. As a result of which, the source has to throttle back the amount of traffic it sends. So this is an important aspect that controlled congestion leverages upon the TCP behavior for introducing congestion avoidance. One other aspect of congestion scenario is the global synchronization. Again, there are thousands of flows out there that use TCP, and when there are so many flows, when congestion occurs at network nodes, the notification goes back to the sources about drops, as a result of which the sources start throttling back their windows, and you see a big dip in the traffic again. So this is a cyclic moment where sources start increasing their congestion window, start transmitting more traffic, and then the notification arrives about packet drops, and then they throttle back. So this impacts network very badly, and this mechanism again needs to be prevented in order to avoid any connection issues because of the TCP slow start mechanism. And so comes in the random early detection algorithm developed by Salif Floyd and Van Jacobson. And it was primarily meant to address TCP, and it tries to use two parameters, the packet drop probability and the average queue size. Unlike the tail drop scenarios where you have the queues filling up, Red leverages upon an average queue size. It tries to actively monitor the queue size and then starts dropping packets based on a certain probability, which in turn indicates the TCP sources about potential congestion scenarios. So some of the TCP sources would be impacted because of the drops, so they throttle back. Instead of the case where we saw in the global synchronization scheme, all the TCP sources start sending traffic at the same time, they realize there is a congestion and they throttle back. Instead, Red uses the drop probability and monitors the average queue size, the two parameters that it uses, and starts selectively dropping packets, as a result of which selective sources are impacted, and so you don't have a similar fluctuation that we've seen earlier. So this is a graphical illustration of the packet drop probability, which is linearly associated with the average queue size movement. There are two configurable parameters, the minimum and maximum threshold, the boundaries that we assign for that particular queue. And as the queue starts filling up, the average queue size, again, the average queue size is being used because if there are any transient bursty traffic, that can be easily accounted for. And it does not, the TCP does not get lulled into the fact that those are, the transient bursts are just vagaries of the congestion conditions, and it's not a prolonged case of burstiness. And so it accommodates for transient bursts by computing the average, it's a weighted average number. And the probability is also a value that can be provided, which determines what's the rate at which the packets can be dropped as the queue size starts increasing, as it starts moving from the minimum threshold to the maximum threshold. And one other aspect that was built upon Red was, now that we have differentiated classes based on the precedence or DSCP values, we should be able to assign weights for different precedence or DSCP types, so that when you have queues for various differentiated parameters, those queues can move appropriately. And for precedences of lower value, you can give them lower thresholds, and for precedence or DSCP of higher value, you can give them higher thresholds, in which case you can preserve the higher priority traffic. So again, this is an illustration of the lower thresholds and the higher thresholds, and how you can have two profiles where you have a standard service and a premium service. The other aspect that QoS tries to, again, factor in is your control traffic. Whenever there are congestion scenarios, your control traffic, your IGP, BGP, all those keep alives and all shouldn't be maintained, and they should not be impacted. So again, various queuing techniques, resource allocation schemes also keep in cognition of the control traffic that needs to be maintained. So when is Red used? Again, as mentioned earlier, it helps in scenarios where TCP is the primary choice of the transport protocol because of the adaptive nature. It doesn't help when it is UDP or the plain IP layer. So with this, we have examined how the IP DivServ architecture has been introduced elements of traffic conditioning, per hop behaviors. We briefly looked upon the different QoS techniques that we can use as part of the conditioning schemes and the per hop behaviors. With this, I'll give it over to Utpal to start the discussion on MPLS and DivServ. Thank you.
Hi, my name is Utpal Mukhopadhyaya. I think I have one of the longest surname. Um, so Arun set up the background for IPQS and what are the QS techniques. We tried not to bring any vendor-specific CLI here to do all those classification, marking, or W rate or MDRR part of behavior. We have various CLIs available. You can configure on the router to do that. We didn't show that. We just tried to drive home what are the techniques you have. And it's a basic introductory QoS techniques. So every vendor has its own way of doing it. So go and apply the rules. We are not trying to address the engineering guideline, how to do, when to do, where to do. But mostly we got the picture that classification and marking mostly be done at the edge. And after you classify and mark those packets, you try to create a power of behavior or PHB, which means queuing or scheduling discipline, as well as how do you drop the packets. So that's mostly on the core side or on the egress side. So when we come to the MPLS, now we can't avoid MPLS domain. We are, let's say, fantastic QoS provisioning has been done in the IP DipServ domain. Now traffic has to go through an MPLS domain. So shall we lose all the beautiful QoS, what we did so far? Answer is no, MPLS as a solution. You tunnel through the MPLS domain. And for that, there is a RFC document. How do you tunnel? What is the interaction between IP DipServ and MPLS DipServ? How do you interact them? What is the what part of information we may lose or what part of information we may gain, what extra tools we get. Let's have a look at that. So once again, primary focus will be on MPLS DipServ. Question, does MPLS introduce any new QoS architecture, just like IPQoS did? IPQoS DipServ went a little bit ahead of IPTOS and did something very good. Answer is no. MPLS really does not bring a new QoS architecture as such. Of course, you have to deal with the MPLS packet, so we'll see what are the tools we have. Secondly, so mostly it is based on IPQoS RFC 2475. Now there is an MPLS DipServ model which was needed to handle packets that are prepended with MPLS level or shim header, RFC 3270. So this is typical an example of MPLS DipServ network, let's say. What's happening? We introduced PE router. This cloud is MPLS cloud. So we introduced a PE router, provider edge. So traffic entering from here is IP. And then we have a P router. It also belongs to the MPLS cloud. This is also another PE router. So we have to do something here. And what we are trying to do, thousands of IP flows will be coming here. And we are trying to use DipServ mechanism. So we'll try to use a kind of aggregate flow. What is the non-aggregate flow mechanism? Arun already touched. You can have a per flow basis, very hard QoS guarantee using RSVP based something. We'll touch that. We need that. But for now, we are talking of DipServ. So basically, we'll be bucketing or aggregating thousands of flows into few simple buckets so that we don't have to deal with each and every flow. If we deal with those buckets, we are fine. So basically, so answer is we can scale well, even in the MPLS world. And what is going to happen here? What is the new thing going to happen? I am entering IP and I am entering an MPLS cloud. This router will be called ingress level switching router. So he has to put two levels, in this case, he has to put levels so that next router switches based on level, not on IP. And the following router, same thing. Finally, IP comes out again here. So let's see when compared to IP DipServ, what is unchanged? Am I going to involve something new here? Probably no. Most of the things are unchanged. So let's see, what are the things? IPDIPSAF talks about traffic conditioning agreement at the edge, talks about part of behavior in the core, or maybe at the edge also. So what are traffic conditioning agreements? Arun already touched. We have classification, we have marking, we have policing, we have shaping. Are those things going to change? No. Buffer management and packet scheduling mechanism, like after you have marked those packets and you are going to put them in an egress queue because you want to treat the queues differently. If you put all the packets in the same queue, how can you differentiate? So you need different kinds of queues. Somebody will be called low latency queue, somebody will be called normal queue. You have to, every packet you put in different queues. And then, depending on how much bandwidth you want to give to your customer, you will be provisioning how much you will be dequeuing from the queue. If you do faster dequeue from a queue, means effectively you are providing better service to the customer. So that's all about scheduling. And he touched upon MDR. And part of behavior definition, again, he introduced the terminology, expedited forwarding, assured forwarding, and best effort, and how they're associated with the real traffic quality. So now let's look at the challenge. I said IP packet entering an MPLS edge router will be creating this kind of packet. What is new here? I still have IPv4 packet. I still have IPv4 TOS or DSCP information hiding here. So I didn't lose them. What I added is this MPLS header. What does MPLS header contain? Of course, I need a label. And to help me out, I have a field called EXP. What does this EXP means? This is basically an IP equivalent of precedence, you can say. 3 bits available. And there is other things which are not important in this discussion, stack pointer and TTL value. So what is the full story here? IPv4 packet came, IPv4 packet came here. This is IPv4 packet. IPv4 header is sitting here with all the TOS and DSCP information. I didn't touch them. I added or appended extra label here, and I had a fantastic tool in that level, one particular field called EXP, which is carrying 3 bits. So you can immediately imagine, since I'll be forwarding based on the level, I have no visibility of the IP packet in the core of the MPLS. Somehow I am obligated to carry the quality of service information that was in that was in DSCP or IPv4 header here into the MPLS header here. I have to carry that. Otherwise, following routers will not understand. They don't look into they have no way of looking past the level and seeing, hey, what IP DSCP field is there, let me act based on that. They don't have any capability. So this is a typical mapping. So let's say I have a expedited forwarding, the best class. Typically it is represented as a 101 and following, this is the whole DSCP value. Look at the EXP field, how many bits we have? 3. I can't leverage all the 6 bits. So let me take whatever precedence value I had, precedence equivalent component of DSCP and map it onto EXP. Same thing, I gave an example, precedence equivalent of DSCP mapped into EXP. You can immediately see the challenge. I am losing information. If in IP DSCP I created so many DSCP points, then I am back to again 8, that's it? Yes. So the question is, this is the problem. So IP DSCP had 6 bits, just because I brought in an MPLS level and which has only 3 bits, I lost a lot of granularity from here. Is there any way we can overcome? There are 2 solutions. One is, well, do you need more than 8 in the code? If the answer is no, live with it. And that approach is called ELSP, means EXP inferred level switching path in MPLS domain. So do all your part of behavior based on the EXP field. What does part of behavior mean? Your scheduling and your drop priority. Because marking and all these things are done already. So you put a CLI that will queue an MPLS packet based on EXP field, and there is a drop field which is W rate. You just put another CLI that, oh, I will drop this EXP0 more, sorry, or EXP1 more than the EXP7. Okay, that scales well. What about if I am not happy with 8, I need more? Well, you can do that. Then you have to take a combination of level and EXP. Because you can't get more than 8 with EXP alone. So you have to tag it up. Okay, take help of someone else together. So that's exactly this picture shows. I have two approaches of mapping. So this is a challenge of mapping DSCP into the EXP field, because I need to forward based on the EXP in the MPLS. So either you take ELSP approach or you take LLSP approach, where you can see that I have combined the level, 20 bits are available, and I have combined EXP. But let's change it to the role now. Level was, use level now as a, for identifying the class, and use EXP for deciding the drop priority. Make sense? And we can scale well with this. Now, is it a very popular model today? Answer is no. Work is going on, but this is not very popular. Still, we are managing so far with this. So now to put the whole picture together, this is just nothing much. This is the whole diagram. Lot of connections are there. ELSR, Edge Level Switching Router. We identified few terminology, and there is another Edge Level Switching Router. So this is my MPLS domain, and this is IP. This is IP. So at this point, I prepended those levels. At this point, I faced the challenge of transferring DSCP information into the level. After that, when the packet comes here, middle routers, he doesn't see IP anymore. He works based on the MPLS packet. And he does QoS based on the EXP bit information that is being carried to him. Okay, so we overcome one challenge. Okay, IP DSCP is bigger than MPLS EXP. How do I map? Next one is MPLS level imposition is not very simple actually, and there are mechanisms that let's say I'll be putting 2 levels. As you know already, some of you or most of you are familiar with MPLS. There are 3 levels in MPLS cloud, IP to MPLS, where imposition happens, and MPLS to MPLS, where swapping of the levels happen, and one final thing, disposition, where you pop up the level and give out the IP packet. Now, everywhere, when you are interacting between DSCP and EXP, you need to have some kind of arrangement, what you want to do. Do you want to propagate all the way to IP DSCP when you go out or not? So there are 3 kinds of modes to figure out the interaction between IP DSCP and MPLS depending on where you are. Are you in the imposition side, means you are adding a fresh level? Are you on the disposition side, means you are throwing away the level and going out IP again? Or you are swapping the level? Because there is a variety of possibilities. RFC 3270 came up with 3 predominant modes: uniform, short pipe, and pipe. Now again, how do I implement the modes? You have the CLI. You can follow any of the modes you like. Depends on your engineering decision, depends on what you want to do. If you don't like uniform, don't do it. Go to short pipe. Do I have the CLI to do that? Yes. You have the CLI to do any of these things. Not directly though. There is nothing called CLI uniform or CLI short pipe. So let's understand what do they stand for. So if you are controlling, you are in charge of the whole DIPSUB domain, MPLS DIPSUB domain, then what you would like to do, keep the coloring information, means whatever MPLS, EXP or DSCP information you have, keep it uniform, like don't change it. Keep it when going from IP to IP, IP to MPLS, MPLS to MPLS, MPLS to IP. Means when you go all these routers who are doing IP to MPLS or MPLS to MPLS or MPLS to IP, don't play with the EXP or coloring mechanism. What does it mean? Let's look at the picture. So here is one of the, again, MPLS cloud is from P to P, and IP is here, IP is here. So as you can see, this router, C, customer edge router, is releasing an IP packet with a DSCP bit 40. Excellent, no problem. It came to PE router. Since this is a layer 3 VPN circuit, he will put by default 2 levels, as you can see, level 1, level 2. Now I did not show what is the level value. That level value will be decided by what level protocol is running here. It may be LDP, CRLDP, or RSVP. Whatever be it, packet will be, IP packet will be augmented by 2 levels. Okay, what do I do now? I came with DSCP 40, I did not touch anything. So I am obligated to carry as it is. Default behavior is whatever equivalent preg, 40's equivalent preg is 5, precedence 5. Why do I say preg? Because ESP field is also 3 bits. And look at that, what he has done. He has encoded EXP5 and EXP5 on both the levels. This is the default behavior. If you want to change by applying a command here to some other value, you can do that. But for the simplicity of the example, I didn't do that. Okay. So when the packet comes out here, this is the story. I have an IP packet, I have an MPLS packet, I have an MPLS packet, and everybody is carrying 5.5. Someone decided to change or touch the EXP field of the top level. Remember that I said you cannot go past all the way here. You can only touch in the MPLS cloud what is in the top. This is a level stack, and this is the top level. Someone decided here to recolor that topmost level. You can touch the topmost level. And as a result, on this side, what happened? All he did, he played with the EXP value here, changed to 0. Somehow he thinks it should be changed to 0. Okay, he did it to 0. Now, bottom level did not change. He is still holding on to 5. Now, by virtue of the MPLS paradigm, we already know that this guy from here to here, he is popping off. When it comes to here, he will pop off. So what is happening at this point? Look at that, what he has done. This was before popping off. If he pops up, then this guy gets exposed. He becomes the topmost level. And before, when it happened, he passed that EXP information to him. Okay, I still have IP packet DSCP 40 and EXP 0. So I am here. Now I am carrying EXP 0 because the top guy passed on to me and before he went away. And at this point, again I will do another popping because I have to go out IP in this cloud. Because this is the IP cloud, MPLS cloud is ending here. So before I pop off, as this is the uniform mode, he also copied EXP0 value into the IP field. So I started with DSCP 40, and when I reach the customer side, it is DSCP 0. And this is part of the uniform field. Question is it a good idea to do that? Depends on, sometimes they need to do that. There is mechanism, and this mechanism is called uniform mode. You are passing the EXP information all the way. Naturally, next question is, I don't like that. Why did I change my customer's precedence field? I have no right to do that. Fine. Then you are talking of short pipe. You do anything in the MPLS cloud, do it. But you have no right to touch my or customer's precedence field or DSCP field, which you saw that DSCP became 0. So this is exactly short pipe addresses that concern. And let me again go to the example. So it won't take, again DSCP 40. By default, there is a typo here actually. Actually, it should be 5.5 because of the previous thing. There's a mistake. And then somebody recolored it, became 0. And this guy is still 5. Don't read it as 3, 5. And then when it went away, it became EXP 0. And when this level popped off, look at that. He didn't pass this information into DSCP field. So I started with DSCP 40. I ended up with DSCP 40. This customer also belongs to the same DipServ domain of this customer. So they see nothing has been hampered to their packet. But in the MPLS code, service provider took advantage of extra EXP-based part of behavior. This is short pipe. So I am retaining the customer's thing. Note that policy applied, PHB of the topmost level is copied in the new top level. Okay, let's go there. Okay, there's one more left. One more left, and that is called pipe mode. Pipe mode and short pipe mode is a little bit tricky. Pipe mode says exactly equivalent to short pipe, with difference of here. Once again, IP DSCP 40, EXP5, EXP5, that is a 2 level. I came here, I intentionally recolored, so topmost level I can always touch. It became 0, bottom one unchanged. Then I popped this level off, I exposed this level, naturally he copied here. And then from here to here, again I will pop this level off and I will go out IP, DSCP 40. So you can see no change, exactly like short pipe. Then what has changed? Change is here. Because remember that this is MPLS cloud. Egress PHB depends not on the IP DSCP 40, but on the EXP0. So this router, the final router who is converting MPLS packet to IP packet, is acting not based on the customer's DSCP, if you want to apply policy here, not on the DSCP 40, but on the incoming DSCP 0. Would you like to do that? Yes, there are some motivations. Why? If you have lots of customers, then you need to know every customer's DSCP value in the previous case. Because if you want to apply a policy based on DSCP 40, as you did in the short pipe mode, then you have to remember all customers' DSCP value and apply policy based on that. But here he is saying, I control this MPLS domain, and I have the full right unto the last mile. And therefore, I will give a QoS based on what comes to me as EXP0, not based on what customer has it. So this is all about MPLS QoS. Now, so we saw two challenges, just to bring back the perspective. If you enter the MPLS world, how do I map DSCP into QoS? And even if after I've done that, how do I handle within the MPLS cloud? There are 3 modes we just introduced. Question is DipServ good enough alone to guarantee end-to-end quality of service? Answer is no. Let's say you have provisioned fantastically QoS everywhere on the link, depending on all traffic type, etc. You have classified, you have marked, you have a beautiful policy working in place. You are ready for the congestion situation. If anything kicks in, it will work. What happens when you thought one link is not a bottleneck and a link failed? Simply, a link failed. And link failure is very common. As soon as a link fails, IGP will try to recompute another best path. So that best path may not be a real best path. It probably went to a very low capacity link. And what was, there was no supposed to be any congestion. Because of your provisioning, you thought I took care. Now because the link became a bottleneck link in the new scenario, it became congested. All the traffic, everybody loves to drive through the shortest path. So we know that QoS alone may not be enough. We need to engineer the traffic. What is your end goal? End-to-end QoS guarantee. So doing only deep serve QoS classification, marking, WDAT, understood. But sometimes it is necessary that you take or engineer your traffic, critical traffic, maybe on the non-optimal path. It may not be the optimal path. Sometimes non-optimal paths are sitting idle. And that's why all of us know that MPLS traffic engineering plays a big role. So why, before I go there, traffic engineering itself is a huge topic to talk. So what I am trying to drive home here, this solution, TE and DipServ together, has a very promising solution. So if we can couple DipServ approach along with traffic engineer, then we can really achieve a very good end-to-end QoS guarantee. So what is the policy of DipServ? What is the extra thing TE is bringing? Spread traffic around with more flexibility. Like you don't have to always go through the shortest path and fight for resources. This is an example, just to motivate what is the traffic engineering. And we all know, mostly just to be in perspective, this guy wants to send 20 Mbps traffic to R5. He also wants to send 40 Mbps traffic to R5. Looking at the topology, we could see that this is the shortest path, right? But what will happen, port link here, he has only capacity of 34 Mbps. So everybody starts trying to send through this path, and nobody notices there is a alternate non-optimal path sitting idle. And as a result, I am happily dropping around 26 Mbps worth of traffic. 20 plus 40 minus the capacity, 26. Okay, doesn't sound good. Can I engineer it? Yeah, this is the beauty of TE. Why are we struggling to send through this non-shortest path? Okay, why don't we send that 40 Mbps traffic through this path? Yeah, it may be non-optimal, but if you have the tool to do that, which is traffic engineering all about, you can direct your traffic like this without any problem. Link will be utilized, no struggling, no fighting for link will be there. So how does MPLS-TE works? First of all, in order for it to work, I need MPLS, I need level. So in the level, now this is a huge area, I want to touch in brief. One thing you can do, you configure a tunnel at the head of a router, and you specify where the tunnel should terminate. In this case, I can see that he is terminating here. So some terminology, that's why you say head end of the tunnel, and the path you are following, this is, you can leave it to the IGP to track down the path, or you yourself can configure, whatever you like. If you tell him go this way, he will go this way. If you tell him go this way, this way, this way, he will go this way. Doesn't matter. But if you leave him, you don't know, because in a real network it may be very complex, and you just don't know how to, what is the best path, or let me ask him, can you find a path to reach here? Yeah, that is called constraint-based routing. And you can also use explicit routing. Now you can have various attributes of the link. IGP needs to know all the good attributes of the link so that he can compute for you. So we know OSPF does on Dijkstra algorithm, shortest path. Now you can extend it and make it constraint shortest path algorithm and ask the traffic engineering tunnel, hey, can you compute for me what is the best way to reach there if I want to meet X, Y, Z, and W. What is X, Y, Z, and W? Okay, I want to set up so much of bandwidth. I want to have a link which has color of all the links that are low latency. I want to reserve for voice over IP traffic. So you have to color the links and tell him that those links only you try to explore. He can do that. And so basically that will be a brief intro. So there is a midpoint. And because of that, because of this tunnel setup, there is a level switched path created. the tunnel keeps on creating level at every hop. So that tunnel has one thing he doesn't understand that to him one link is one link. He doesn't understand link has so many flavors. Regular TE or regular traffic engineering, you can have only one reservable bandwidth. But we are introducing a new terminology, and this is the final thing in this talk, deep serve aware traffic engineering. What does it mean? Let me take help of a picture, it will be clear. Okay. So what you are doing here is from here to here, I have two paths. Why don't I color that the best effort path is along this one? Means I don't really care about QoS. And I set up another path for critical applications like voice over IP. So this is one other way of winning the QoS battle, am I right? DeepServe, we created classes and everything. How about if we really can redistribute traffic across the network, taking help of traffic engineering tunnel, and direct some best effort traffic one path and voice over IP another path, and like that we can keep on creating different flavors of traffic engineering tunnel, then we can map various applications onto the different tunnels, and we are fine. Remember that traffic engineering tunnel has one more powerful feature which IP doesn't have, is if the link fails, he can automatically take care of it through the node protection or link protection if you provision for that. So that means this is my link capacity, and I created 3 different classes of traffic, red, yellow, and blue. These classes are not the same as Arun touched or DSCP based. These classes means traffic engineering classes. That means I am making the link super smart of understanding 3 different flavors of traffic engineering requirements. So again, in order to do that, you can have, basically there are 2 models today are used in IETF. One is maximum allocation model, MAM. Another one is Russian dolls model. So once again, this is the whole link. And there is a class 3 traffic engineering tunnel, class 2 traffic engineering tunnel, and class 1 traffic engineering tunnel is the blue one. So all that means, look at that, I can reserve for BC2 30% voice. What does it mean? What is it trying to say? Say, I am creating a traffic engineering tunnel, which is very critical, will exploit different sets of links, and I will map my voice traffic over that. Why should I do that? Because in the event of voice is a critical application. If there is a failure on the tunnel or link, I can do lot many things with that. I can reroute, I can do node protection, I can do fast reroute, etc. Then I am creating another traffic engineering tunnel where I am reserving 50%. That tunnel I am reserving 50% for premium traffic. Now note that they are all same link, 3 different traffic engineering tunnel. So I am creating per class traffic engineering tunnel concept. And all of them together should definitely summarize the total link capacity, maximum reservable bandwidth. There is another approach. So what is the good thing about that or bad thing about that? If due to any reason this link, this is your real link, 30% of the link you have reserved for voice, and you are not using voice, there is no voice traffic, well, it is going wasted. Suddenly you see there is a more than 50% premium traffic, and just because it is a hard reservation, just because you have reserved 30% for the voice and no voice traffic, he cannot go and encroach this. So I am wasting my bandwidth here. What is the good part of it? Everybody works independently. Like just to provision, I can provision here, I won't disturb him. If I don't, I cannot super provision him. If I try to take away some tunnel from here, I won't disturb him. So they are independent, they are sitting side by side without impacting each other. So to overcome the bandwidth inefficiency or utilization problem, they said, why do you do that? Why don't you encompass this model? that you create a tunnel based on BC1 capacity that will cater for both class 2 and class 3. Meaning, if class 3 traffic is absent, well, whole class 2 will take advantage of it. If class 3 is present, he should be able to throw away or knock down some of the class 2 and take his power, take his control. So in that way, I won't be really wasting my bandwidth here. Because if no class 3, I can take advantage of full class 2. If class 3 is there, he still wins, knocking me down some of the class 2 existing tunnels. He will bring down. Same model, so one within the other. So this is kind of Russian doll. This is within this is within this, and one within the other model. So this is a good part, good bandwidth utilization for creating traffic engineering tunnel. But the bad part is you will be tearing down some of the tunnels of class 2 if you want to provision class 3. And you feel the need that so far premium traffic was happily going, utilizing full capacity, and suddenly someone decided, oh, I have a voice traffic coming. So I need to set up voice and then bring down some of the premium traffic. So this is the kind of concept when deployed on the network. You can see the various colors in the tunnel. All that means from here to here, you are creating 4, 5, or maybe up to 8 different classes of tunnels. You can keep creating here, same as here. What should I do with those tunnels? Remember those tunnels, you will be mapping your traffic, the best traffic on the best tunnel, second best on the second best tunnel. And in the process, because traffic engineering gives a lot of powerful feature like link failure protection, that I won't lose you, less than 50 millisecond guarantee and everything, you can really give an end-to-end QoS guarantee by exploiting traffic engineering. So this is basically same kind of configuration. So bottom line, does that preclude me from configuring classification, marking, and all these things? Answer is no. So you are bringing one extra dimension of traffic engineering, but still you have to make use of the deep server QoS techniques which Arun taught, or in the context of MPLS, whatever I touched. And together, you can really, really offer a good end-to-end QoS guarantees. So I think, sorry, traffic engineering is a huge area. We have to make it short for the time thing. And this is where we will wrap up our summarization. So what did we learn in this? First of all, the QoS techniques, like what it told. Today we really do. When we apply QoS, or you engineer QoS, you have to apply classification. You have to identify which packet should you give priority, which packet you should throw it away, which customer is paying you a high premium, which customer is not paying you. Based on that, how do you identify that? He told you the techniques. Look at the source address, look at the destination address, look at the port, source port, destination. You have so many tools to identify or classify that, okay, these guys are good guys, I have to tackle them differently from other guys and giving them more priority. So to do that, we introduced the IP DipServ model. We have, he touched upon, we have an integrated services model as well. But we didn't delve much into that because it doesn't scale really well when you have thousands of flows. But it's really good for per flow model. You have very few flows and you want to give a very good guarantee, RSVP is the best because he is reserving bandwidth. Then we extrapolated the concepts into the MPLS world and we put the challenges. If we bring IP into MPLS, what are the new things? A lot of things are common. New things, as I showed you, how do you map DSCP into MPLS EXP? And second problem is within IP to MPLS, MPLS to MPLS, MPLS to IP, what are the techniques you want to use? You want to copy the EXP field all the way to IP DSCP or you don't want that? Its choice is yours. You have tons of CLI. Various vendors have different way of implementing it. Just use it. This is your engineering decision. Call is yours. Then that's exactly the last but one bullet, DipServ tunneling modes I touched. And finally, to make the QoS look good, so why don't we exploit part of integrated services approach like RSVP-based traffic engineering tunnel and use the deep serve approach also, so that we have a end-to-end IP, MPLS, traffic engineering, end-to-end good QoS story. So there can be end solutions. I didn't bring any demo like how to engineer or configure depending on what is the criticality. If you are provisioning for stock codes, real-time application, you'd like to pass all these things through the low latency queue where there is hardly any latency, delay jitter. They are treated fast. That is called the scheduling mechanism. Every router will have that. You can have it in software. You can have it in the router hardware. Because of the speed these days, I work in the core routing platform, and we provision everything in hardware. So you can really touch those queues and you provision whatever you like. And then next best traffic you put in the next queue. And once you have decided that I will put the premium services on the low latency queue, and then other services in the queue number 2, 3, 4, next challenge comes for you, okay, how much bandwidth you are giving? Now he needs 30% bandwidth for voice, he needs 10%, he needs 1%. The dequeuing algorithm, how quickly, how fast you dequeue, that is your MDRR needs. That guarantees you the bandwidth. Okay. Third approach is, even then you cannot guarantee congestion. You dequeued, fine. What happens if the link is congested by some misbehaving guy? So in that case, I have to drop. Now, drop cannot be random. Then you'll have everybody will suffer. So you look at the, again, DSCP field and say, okay, this DSCP is a good guy. I will drop him less. This DSCP is a what's offending guy, so I'll drop him huge amount. How do you drop? He already touched. You control the queues, minimum threshold and maximum threshold. So as I said, I map the traffic into queue. Now queue is unique. Now queue you can say, okay, from here to here, if I reach this watermark, I'll start dropping. So again, it is your call. Where do you want to drop and how do you want to drop? And sometimes you may be lenient, saying that, well, I won't drop you, you are misbehaving fine, but I can take you because there is no network load. So I can take you. So in that case, you put it on a lower priority queue and dequeue from there. And I think that will be all. So if you have guys any question, you can ask us. Thanks for your time.
Question for you, Fred Wetling from Bechtel. You guys have described the agony that you've gone through trying to navigate within the 8 bits allocated for the toss byte. With IPv6, we have a 20-bit flow label. Talk a little bit about what you're going to be doing with the implementation of this type of control, the MPLS and so on, within the context of V6 and the expanded space that you have to identify different types of traffic.
In the V6 traffic process.
Well, we wanted to sort of limit the discussion to V4. We are not fully conversant with the V6 aspect of it, so we may not be able to provide you the best answer possible. So I hope that will be okay. Thank you.
Okay.